There might be more people. All right. Hi, everyone. Welcome to the second talk on a seminar series on optimization, algebra, and geometry. We are pleased to have Alexander Strang from University of Chicago. Alex is going to talk about the functional theory for principal trade-off analysis.
Okay, thank you very much, Ali. So this is joint work I've been doing with some collaborators at LAIC, that's Lockheed Martin's AI and sort of computing group. And today I'd like to walk you through an embedding method which attempts to encode strategic information in decision problems or games in terms of geometry, and that method is based on solving an optimization problem. So I'll start with some motivation, I'll go through the background here, and then we'll be able to move on to the meat of the talk. So the motivation for this talk, our goal is to construct a latent space representation of generic two-player zero-sum games that satisfy sort of a list of design criteria, essentially. So I'll walk you through these one by one. So first, we aim to represent some arbitrary, potentially very complicated game as a combination of simpler canonical games, where we can control the properties of those simple games, and in particular, where each of those simple games is visualizable. So we aim to construct a series of simple canonical games where each game can be represented in a space that you can visualize. And then whatever strategic information is encoded in the original game should be then subsequently encoded in the geometry of these simpler games once we map into those simpler games. So really this goal of making a generic game visualizable means that we need to encode strategic information as geometry so that it's something you can visualize. Because we are hoping to represent something complicated as a combination of simpler things, there's also naturally a model reduction story here. So the number of simple canonical games that you use, you could think of some measure of complexity. And if you truncate the sequence of games used to represent the complex game, then that allows some sort of model reduction, some sort of dimension reduction into this problem. In addition, we would like for each of these underlying simpler games to have some sort of interpretability. And this isn't guaranteed, but this has often been true. And this is where the name sort of principal trade-off analysis comes from. It's the idea that essentially each of these underlying simple games will act like some fundamental decision trade-off that combine to produce the overall game. So sort of this is, in some ways, this is a representation of a generic game in terms of combinations of trade-offs, where each simple game models one specific sort of feature trade-off or principal trade-off for the overall problem. Once this is accomplished, then these methods enable sort of further investigation. So once we can visualize and represent games in this way, then we sort of have a unified way of representing games in terms of this sort of simple combination of simpler games. And so that enables game classification. It points towards different methods for game construction. It allows interpolation and extrapolation of advantage relationships based on sample data. This is particularly important because most complicated games, you don't actually know them sort of functionally, you only know them through sample data. And that interpolation and extrapolation is useful because it would let you take information that you maybe can infer or guess from this representation and use that to guide training. So there's some suggestion that this may be helpful in agent training. This approach is relevant to a wide variety of areas. So you can think that games show up sort of across the sciences. They appear in natural competitive systems and sport analytics, social choice, global politics, sort of take your pick. A number of general decision tasks can also be cast as games. So the techniques used here can also be thought of as useful when trying to understand decision tasks, maybe like in operations research. So here, the methods that I'm going to be showing you today, these are sort of strongly inspired by some work out of Google DeepMind. This is work that they published sort of starting in 2018 through 2020 on trying to represent tournaments among AI agents, so agents they were training, and try to represent the structure of the game and the optimization problem in terms of something that sort of has these nice properties. So with that objective stated, let's sort of state the domain, the things that we're actually going to treat. So the types of games that we consider are functional form games. These are two-player, zero-sum games where performance or payout is a function of your agent attributes. So we start with some attribute space, omega. And here, this could be multivariate. These could be, you could think maybe physical attributes of agents. These could be probabilities of maybe particular choices. So these could be behavior probabilities, or they could be parameters that parameterize the behavior of an agent. So for example, weights in a neural net that parameterize how an agent whose sort of behavior is controlled by the neural net actually behaves. Then in addition, we have some sort of performance or payout function, which accepts the attributes of two different agents and returns the advantage that one possesses over the other. So this will represent with F. This is a mapping from omega cross omega into the reals. And we require that it satisfies this fairness criterion, that is f of xy equals negative f of yx. This essentially says that the two players are symmetric, that there's no specific role that's distinct between the players based on the order in which they're listed inside this function. And because we require this sort of skew symmetry, this is equivalent to looking at generic zero-sum games, zero-sum two-player games on possibly continuous strategy spaces. Now, in practice, most games of interest do not have sort of a known function. In most empirical games, you need to estimate this function f, and you need to estimate it based on sample data. So the other natural topic here is empirical game theory, which is really the study of a game through observed or sampled gameplay. Empirical game theory has somewhat different goals than classical game theory, because in the empirical setting, you're really focused on characterizing a game as it is actually played by the players playing it. So you have some population of agents who play the game, rather than trying to find some idealized or optimized agent. All right, so that's essentially the domain, the topic that we're going to be trying to address with this representation. And note that everything I say today, even though all of it will be couched within the language of games, it will also apply to general decision tasks, because general decision tasks can be often sort of cast in a way where they take on the structure. Really, all that you do is you exchange the notion of an agent for the notion of an object or a choice, and you exchange the notion of performance or payout for preference. So those are the generic games. Now let's focus on our simple canonical games. These are sort of the atoms or the building blocks of which we'll try to build up the molecules of a more complicated game. So we'll start with what's called a disk game. And this you can think of as sort of a canonical cyclic game. This is like the simplest cyclic game. And it's essentially just a continuous extension of rock, paper, scissors. Here, the functional form acts on vectors taken from a plane. So we start in R2 and just evaluates a cross product between them. And this is sort of a natural game to work with because it models a trade-off between two different traits or two different attributes. Here, whenever I draw this, I'll have this sort of background circulating vector field. You can actually generate this cross product by taking path integrals against this vector field. So in some sense, you can think that advantage acquired by one agent over another, you could imagine as being sort of pushed or comes from this flow in the background. And you can sort of see here that advantage will flow around the origin. In that sense, there's sort of a natural sort of rock, paper, scissors dynamic happening here, but it's happening continuously. Now, one of the motivations for working with the cross product is the cross product is a deeply geometric operation. So I'd said at the beginning that not only do we want simple games, but we want games where strategic information is encoded visually. That means that we want whatever this function f is, we want it to be defined by as geometric an operation as is possible. And the cross product is a great candidate for that. So you can sort of spell out a whole series of strategic statements about this game entirely in terms of geometry. So for example, the value of this function between y and z is just the signed area of this triangle. Moreover, advantage flows downstream in the direction of this current. So advantage is maximized by moving 90 degrees downstream and would be minimized by moving 90 degrees in the other direction. So that naturally points you in the direction of exploiters. And there's a much richer geometric story that you can use to try to interpret the strategic information when we try to embed into these spaces. I'd be happy to go through more of that later, but I think for the sake of this talk, I'll assume that you're familiar with cross products and we'll keep moving forwards.
Sorry, can you explain where this vector field is coming from? I think I missed that.
Yes, so this vector field right now, this vector field is used as a visual way to represent the cross product. So if I wanted to evaluate the cross product of y and z, that would be equivalent to evaluating the line integral going from z to y against this vector field. Right? So you can sort of think that like, if you want to evaluate the cross product on an edge between 2 points, that really all that you need to do is you need to visualize sort of computing the work it would take to move against the vector field along that line.
Okay, all right.
And there's actually a much deeper interpretation of this vector field. Hopefully we'll have time to get to that to the end, but for now you can think it's sort of just it's a visual aid to help you visualize the cross product.
All right, thank you.
Okay, so those are the building blocks. Now we want to represent something generic in terms of these building blocks. So what we're going to look for, and this might be familiar to you if you're familiar with things like reproducing kernel Hilbert spaces or kernel methods. We're going to try to represent a generic game by mapping from the trait space into a new space where the generic game after that mapping is just a sum of disk games. So we'll introduce a map Y that maps from omega into R2D, where D is the number of disk games that I'm going to use. And I'll treat this as a sequence of D planar embeddings, where I have Y to the K, that's the kth embedding, is mapping me from omega into a plane. So that has 2 coordinates. And this is just some generic mapping starting in your trait space. So mapping from agents as they're originally parameterized into a new coordinate system, really into a plane where I'm going to apply a disk game dynamic. Then my goal is to recover the performance function F as a linear combination of the disk game dynamic, that cross product, applied to each of these different mappings. So you imagine you could start with some population. That population, each individual has a set of traits. So you can map each individual into a location in a disk game. So that's what the point clouds sort of drawn down here schematically represent, that these could be the mappings of a population into 4 different planes. We then apply the disk game dynamic. So for example, if I wanted to find out what is the performance relationship between these 2 nodes on this edge, well, then I would just take the cross product between these 2 points, and then I add that up across all of the different disk games. And my hope is that that recovers the generic performance relationship. So I'm trying to represent a generic function by mapping into a space where that generic function becomes a combination of cross products. And that's fundamentally the problem. Given a function F and a space omega, find this mapping. And obviously there's an existence problem here. There's a question, does this mapping exist? There's also an estimation problem. If we don't know F exactly, can we approximate it using this type of construction? So to emphasize some of the virtues here, this approach achieves most of those design criteria I'd spelled out in the beginning. So each individual disk game, or some truncation of it, some combination of the disk games, acts like some latent space that's representing the original functional form of game, in a way that's here sort of analogous to kernel methods that just exchange an inner product for a cross product, where the coordinates in the latent space have direct strategic meaning because I'm using a geometric operation. I'm using that cross product to define performance within each plane. Moreover, because each embedding is planar, I can plot it. So you can actually look at these things. And the visuals are interpretable, again, because I'm using this cross product, again, because I'm using an operation that you can actually visualize and read structure from geometry. We can think that each of these different embeddings defines essentially a mode of cyclic competition. And that since each of these is sort of modeling a trade-off between the 2 axes, we can think about these as sort of principal trade-offs that combine to add up to whatever the overall trade-offs or dilemmas there are in the game. And it follows that the number of required embeddings or modes is sort of the latent dimensionality of the cyclic component of this game. So that's the objective. Let's look at the simplest case. So the simplest case here, this is what's called principal trade-off analysis. This is limited to pointwise embedding. So this is a situation where instead of trying to embed an entire function, you just try to embed samples from that function. So if I start with some ensemble of agents, I have some population here indexed by I, then imagine that we evaluate performance between all pairs of those agents. So I can make a matrix then whose ij entries are the advantage that agent I possesses over agent j. This matrix is real and skew symmetric because the original function is skew symmetric. And these entries may only be known up to some noise. And it's possible that in certain situations you're missing entries. In fact, that's the generic situation. There are other methods to handle that. You can do matrix completion beforehand if you like. I'm not going to talk about that during the talk today. Our goal, just starting in this pointwise setting, is to recover a pointwise embedding that maps from the indices, so like an index for a particular agent, to their location in this sequence of planes. So what I'm trying to do then is essentially perform a matrix decomposition. I'm trying to recover this matrix, capital F, from some matrices, capital Y, that are essentially samples of some unknown embedding function evaluated at each of the agents. This can be accomplished, and really all that you need to use is...
Can you also explain where these empirical performance metrics is coming from? Can you?
So in practice, this comes from observing events. So the idea is that you have a population of individuals and you observe events between them, and you've defined this performance matrix or your performance function as some observable that you could estimate often given an infinite number of observations of the game.
Right.
So maybe
does it have anything to do with the matrix compilation problem? Because I mean,
yes. So if you are missing entries, right, from this matrix, then the method I'm going to show you on the next slide, this requires having a complete matrix. So you would need to use matrix completion at the start to fill it in. The functional approach actually does not require matrix completion, because essentially the functional approach will treat missing data like randomness coming from a Monte Carlo approximation, and then it doesn't require performing matrix completion at the start.
all right, thank you.
Okay, but yeah, and so if you're used to thinking like performance is preference and you're thinking preference data, this should be very similar to thinking like you have a big matrix with individual preferences, and you would often in that situation be missing a lot of entries. So here, this is possible, and it's generically possible via a classical matrix decomposition. So if I start with some real skew symmetric matrix A, then I can represent it with what's called the Schur real form, where I break it into Q, U, Q transpose, where Q is an orthonormal square matrix and U is block diagonal. This differs from an eigenvalue decomposition in that U is block diagonal, not diagonal, and U is real instead of complex. So here, the diagonal entries of U, we have a series of 2x2 blocks, where each 2x2 block is a little rotation matrix, and that generates the skew symmetry of the original matrix. And then we weight these diagonal blocks by the magnitudes of the eigenvalues of the original matrix. If you like, you can recover this decomposition directly from the eigenvalue decomposition of the matrix, or actually from the singular value decomposition. It's essentially just a rearrangement or permutation of some of the columns of a singular value decomposition plus an extra negation step. And in some ways, I think that really this is, if you want a spectral representation of a skew symmetric matrix, I think this is honestly the most intuitive or most natural form, because we explicitly represent rotation with a little rotation matrix, and this operation is essentially breaking the matrix A into its action on a series of orthogonal planes, where within each plane we perform rotation. Now, here, one nice thing to note about this decomposition, because it is equivalent to rearranging an SVD, truncation of this product at a finite incomplete series of these diagonal entries actually produces the best rank, low rank approximation of the matrix. So if you write this out as a sum and truncate it at D terms, you're actually producing the best rank D approximation to the original matrix in Frobenius norm, because this is equivalent to the approximation you would get from truncating the SVD. Now we can use this decomposition to generate our pointwise embedding. So if I start with a function or a matrix F, it's real, it's skew symmetric, so I can Schur decompose it. And then I can immediately write down what my embedding, the columns of that embedding matrix need to be, just by extracting the columns of this Q matrix and then scaling them by the square root of the corresponding eigenvalue. And you can check that if you take the matrix defined in this way and evaluate this sum of cross products, then this is equivalent to performing the product QU, Q transpose, so you recover back your original matrix. And so this tells us that upon restriction to a finite point set, all functional form games admit a disk game embedding, such that the performance between traits in the point set is a linear combination of disk games applied to the pointwise embedding. So essentially this says that if you're given pointwise data, this is always possible, and all that you need to do is perform the Schur decomposition. So here, because this is based on a spectral decomposition, this embedding will inherit all the nice properties of the matrix decomposition. So in particular, just like SVD, so just like PCA, principal trade-off analysis produces a sequence of embeddings that are orthogonal to each other. So in some sense represent independent cyclic modes underlying the game. And so we'll think about these as being the principal trade-offs. In addition, they form a low rank optimal sequence. So truncation at a finite number of these disk games gives the best low rank approximation. So that allows model reduction, allows some measure of complexity. And moreover, we can quantify the importance of each of the disk games just by evaluating the corresponding eigenvalue. In terms of the visual, that corresponds to sort of the total area, or really the variance in the scatter cloud when I embed into each of these different disk games. So you can just look at them, and the amount of area spanned by a scatter cloud tells you how important that individual disk game is. let's look at some examples here. So this is an example applied to Pokemon. These are some sort of just mathematically constructed examples, but let's apply an example. It's a sort of a more interesting case. So in this case, we trained a series of RL agents to play as different Pokemon in the Pokemon game. And this was a nice candidate for something that might be well represented by this technique, because you sort of have natural hypotheses about what the trade-off should be in a game like Pokemon. What we actually see is that this first disc game, this is essentially a transitive game. This is a game where advantage carries you from one end of this curve all the way to the other. And because this curve does not wrap around the origin, moving in this direction exclusively confers advantage. This is essentially moving from rock to scissors in absence of a paper. Here, this coordinate directly corresponds to the speed of the agent. So there's an extremely strong correlation between your position along this curve and the speed of the agent. So what this extracts is basically the result that speed corresponds to agent quality, if you just take sort of average agent quality. The next disc game falls naturally into clusters. So this falls into a series of clusters. And if you color the agents by their type, whether they are fire Pokemon, water Pokemon, grass Pokemon, and so on, you find that these clusters are exactly the clusters corresponding to type. So absent any actual information that the Pokemon have type, just looking at evaluating their performance, you recover these clusters. And moreover, the relations between these clusters generated by applying the disc game, that's what's represented in this matrix here, recovers the design parameters, the designed relationships between those types. So the locations of these clusters in this plane actually recovers the relationships that were baked into the design of the game. This disc game was sort of surprising to us at the first. It just looked sort of like a cloud. But when we color the agents by their generations, so Pokemon have been released over a series of generations, then there's this clear gradient from old Pokemon to new Pokemon. What's particularly interesting here is this reveals a design choice, because this means that every time you move up one generation, so if you go from like the previous generation to the next generation, the Pokemon in the new generation do a little bit better than the Pokemon in the old generation. But on the whole, the overall game balance is not upset, because the newest Pokemon are actually tend to lose to the oldest Pokemon. And so this you could think is actually design criteria. They're trying to solve the problem of how do you introduce a new set of players that your actual human players want to use. Well, then they need to be better than their current generation, but that don't result in overall just inflation so that older generations become irrelevant. And that trend where new beats old, but in this sort of cyclic fashion, that's repeated within each type. So you can actually see that within each type, the newest generation is better than the oldest generation, but that doesn't upset the overall balance of the game. So this is just an example of how this type of analysis can encode strategic information in geometry, and how that geometry can be read to discover sort of underlying fundamental trade-offs about the game. Now, this approach has some limitations. First, everything I've said so far has been limited to sample data. So we don't have the ability to embed functions. And that really is limiting, because in a series of sort of example tests that we've tried, it's very clear that if you increase the number of sampled agents, the point clouds that you're embedding are converging to some function, but it's unclear what that function is. Moreover, if we only embed pointwise, we are not able to interpolate or extrapolate based on that sample data. So we can't infer performance between new agents. And this is really limiting. And once you start playing with these embeddings, you immediately see that there's some underlying function theory going on here that is not well described by only thinking in a pointwise sense. Because if you only think in a pointwise sense, you are really limited to thinking in terms of what you've sampled. And the approximation theory, the robustness of these embeddings to who you happen to sample is difficult to study if you don't have a background functional theory that you can treat the pointwise theory as a restriction of. So the goal for the rest of this talk, and really what's new, is to try to pose an optimization problem so that we can solve for those embedding functions themselves. So here, this is going to be our objective. We'll let script y denote a finite vector space of functions, where each function y within script y is a mapping from omega to r. Obviously, there are all sorts of classical function families you could think here. You could use polynomials, you could use Fourier series, piecewise polynomials, wavelets, really whatever you like, whatever function space you sort of can imagine that you think might be relevant. There are reasons to pick different function spaces depending on the game or the decision task. So for example, if you're looking at a finite extensive form game, in some sense, polynomials are kind of fundamental. I'll show you some examples based on the Blotto game later. Blotto is an example of a translationally symmetric game. So if you know certain symmetries of the game, that can be useful. And if the game is symmetric, then actually the relevant sort of family of functions you should be looking at are things built out of Fourier series. Then again, we'll introduce our embedding map. That's a function that maps from omega into a sequence of planes. And our goal is to pick an embedding map where we constrain each individual embedding to come from our function space. And we'll try and minimize the expected square error between the disk game dynamic applied to that embedding map and the original performance function. And here we'll evaluate this expectation over randomly sampled pairs of agents, where those pairs of agents, that's X and Y here, are drawn from some population. So we imagine we have some distribution pi modeling our population of agents. We can sample agents from that population, and then we're going to look for an embedding map that minimizes the expected square error between F and the disk game dynamic applied at those pairs of agents. Part of the motivation for including this distribution is this bakes in a lot of flexibility into this method, because if I restrict this distribution to be just, say, a series of sampled competitors, then this objective function is exactly the same as the Frobenius norm error of an approximation of the evaluation matrix. And so actually one of the things you can prove once you've solved this problem is that this functional approach completely envelops the pointwise approach via restriction of pi here to an empirical measure. Okay, to solve this problem, really, we're just going to work with some tools from Hilbert space. So we need to define a Hilbert space. So we'll introduce again our domain omega. So that's the space of possible agents. And then we'll introduce that distribution or measure over the domain that controls where is important in the space, where do we want our disk game dynamic to accurately recover the function f. Again, that absorbs this pointwise special case if I use an empirical measure. And then once I have this distribution over omega, I can start to define products. So I can define an inner product and the associated norm. And this is sort of not surprising. This is the way you would usually define an inner product. Here I've written pi as if it was a density. This doesn't have to be a density. And once we've defined in an inner product like this, then we can build orthonormal function bases. So if I start with script y, that finite dimensional function space, I can use Gram-Schmidt to build an orthonormal function basis for that function space, where orthonormality is defined in terms of this inner product and in terms of this norm. This will serve essentially as a basis for the embedding maps. So I will try to construct my embedding maps out of combinations of these basis functions. Then we can also map this measure in these products up into the product space, that is omega cross omega, which is where the performance function acts. Remember, performance is evaluated on pairs of agents, so it acts on inputs from the product space. Well, we can easily define an inner product on the product space just by using the product measure and an associated norm. This norm is essentially, again, this is evaluating the expected value of f squared when you sample x from pi and y from pi independently. We can also introduce an outer product, which takes us from a pair of functions, each acting on omega, to one function that acts on omega cross omega. And you can think that whenever you're applying a disk game sort of dynamic to an embedding map, you're creating a linear combination of outer products. And so in some ways, what we're trying to do is we're trying to represent a function on the product space as a linear combination of outer products of functions on the original space. This is very analogous to low rank approximation of a matrix. We're trying to represent a matrix that's a function of two indices as a linear combination of outer products of vectors, which are functions of one index. And actually the method, once we've sort of performed projection into our finite dimensional function space, will boil down again to a matrix decomposition. Once we've defined this outer product, we can also define an associated orthonormal basis of outer products that's generated by taking all of the outer products of our basis functions that we'd used to essentially build up our function space Y. Now, given these tools, it's actually pretty straightforward to solve that optimization problem that I posed. So first, you use Gram-Schmidt to construct an orthonormal function basis for the function space of embeddings. Then you project your original function f onto the span of the product basis, and that produces a matrix C whose coefficients Cij are just given by a series of inner products evaluated in that product space. So these are inner products between F and the outer products of the basis functions. And you build that up into a coefficient matrix C. Then you Schur decompose the coefficient matrix. This is exactly the same thing we did when we had originally our performance matrix. And then you can embed, and actually this is essentially exactly the same construction that we'd use in the pointwise case, except instead of embedding pointwise, we take the Q matrix from this Schur decomposition and the eigenvalues from the Schur decomposition, and we combine them with the original basis functions to produce our embedding function. And so this is very straightforward. This is a very nice algorithm to analyze because things like the error in this approximation come entirely from this projection step. This is just projection onto a function space. So that's very classical. That's very easy to analyze. And it's also fairly easy to analyze things like stability. You can build a rigorous approximation theory here because really each of these individual steps is strongly classical. You're computing a sequence of inner products, you build those up into a matrix, you apply a spectral matrix decomposition, and then you take linear combinations with those coefficients to build up your embedding map. Okay, so I see that I'm at 30 minutes now. So here, I'll go through sort of some of the main points here and then stop, so we'll have time for discussion.
All right, before you go on, do you have any complexity results for the algorithm?
Do I have any
complexity result? I mean, so.
So I don't have complexity results. Here, I would say that, I guess we haven't thought about this in terms of computational complexity, in part because usually the empirical limitation is your knowledge of this function f, which you're restricted to samples anyway. And then the challenge is really getting enough information, enough sample information to estimate these inner products robustly. So I haven't thought about this in terms of complexity yet, because we've been focused on essentially the approximation theory, which has been more of a statistical question. Because when you don't have this function f exactly, then you are restricted to approximating these inner products with essentially Monte Carlo estimates. Mm-hmm. And then you need to be able to, essentially what you want to do is introduce tail bounds on the errors here and then propagate those through to the embeddings. So that's sort of been the focus of our practical work on this. In practice, we've never been in a situation where this has been a computational complexity challenge. So in none of the examples that we ran, have we ever had an issue where it just takes too long, which is part of why we haven't been motivated to look at complexity. Certainly, if this matrix C was extremely large, this operation will be slow. But generically, you sort of don't want this matrix to be too large because this matrix has size equal to the dimension of your function space. And if you allow your function space to be too generic, it's difficult to project onto it robustly. You essentially get an overfitting problem. So we've had much more of an issue with stability than we have with computational complexity.
So what do you mean exactly by stability here? Because you use it several times, but what do you mean by stability, like for this algorithm?
Sure. So by stability, I mean, you could ask essentially, suppose I sample one set of agents and I sample a different set of agents. And based on each of those samples, I observe some events, and then I use those events to estimate f at a series of pairs, which then lets me estimate these inner products essentially in a Monte Carlo fashion. That gives me two different Monte Carlo estimates for these coefficients in this coefficient matrix. And if there's randomness in who you sample, those estimates are random and will be different from each other. So then you can ask how stable, how much do the resulting embeddings react when you change who you sample? So how sensitive are the embeddings to changes in the sample population, right? So, and then you can ask sort of how stable is this with respect to changes in who you sample, randomness in the sample pairs, randomness in the estimated values of f based on the outcomes of events, because your event outcomes may be stochastic. You can also ask about stability or sensitivity to changes in this function basis or changes in the dimension of the function basis. And all of this you can actually treat analytically, really, because each of these steps by itself is classical. So you kind of build a machine where you analyze sensitivity one step at a time, and then you can sort of propagate some sensitivity statement from one step of the algorithm through to the end.
Mm-hmm. All right, thank you.
Okay, yeah, so maybe here I'll just emphasize, so very quickly, this functional approach, it inherits all of the nice properties that the pointwise approach had. So again, each embedding has some notion of importance that we can compute directly from the eigenvalues. Each embedding is orthogonal to each other, so we have some notion of independence between these embeddings, and this produces a low-rank optimal sequence. So if you truncate the functional approach, you build a low-rank optimal estimate to your original function. You can prove an addition, you can prove uniqueness. We can come back to this if you're concerned about uniqueness. The last point that I'd like to make here before just turning this over to discussion is that the embeddings that this produce are really sort of fundamental objects. And they're fundamental because they're tied to the eigenfunctions of an operator that's defined in terms of this function. So if I start with a function f, I can treat that as a kernel for an integral operator. So I can define this integral operator, capital F of g, which just integrates g against f in this measure. And it turns out that the embeddings that you produce using this functional approach are exactly proportional to the real and imaginary parts of these eigenfunctions. And so there's actually a deep connection here to Hilbert-Schmidt theory and like eigenexpansion and all of the classical stuff from function theory. And that leads you immediately to some really nice statements. So for example, any function f that is finitely disgame embeddable corresponds to a degenerate kernel in some integral operator. And moreover, any function f, when treated as the kernel of an integral operator that admits an eigenexpansion, is also disgame embeddable. And so this lets you state sort of certain like universal approximation results in terms of classes of kernels that admit an eigenexpansion. Okay, so there's certainly more I can say here. I have more slides, but I think at this point, let's turn over this conversation to questions. I'm happy to show an example of this if you'd like to see a specific example, or I'm also happy to talk through sort of the differential geometry associated with these maps. But I think let's turn that over now to your curiosity.
All right. Let's thank Alex for this wonderful talk. So we have a few minutes for questions. Is there any question?
Yeah, so Alex, just a very vague general question. So if I understood you, that the scope of this theory is what, 2-player zero-sum games of perfect information? That's the kind of setting?
Yes, yeah, that'd be correct.
So is there any prospect of extending to larger classes of games that in any direction? That's
so I think perfect information may be treatable. Breaking out of the 2-player zero-sum setting is difficult because a lot of what is said here, like this relationship to the eigenfunctions, is really tied fundamentally at some level to the idea that you can treat this function as the kernel of an integral operator.
Yeah.
And then things like the representation with a cross product really have to do with the fact that this operator is not self-adjoint, but is skew self-adjoint. Right. And that skew self-adjointness, that's kind of a fundamental property of this operator that would be lost if this was not a zero-sum game.
Yeah.
Right. So that. Yeah. So that is true. Actually, I should actually back up from what I said earlier. This does not require perfect information. So this does not require perfect information. Really, all this requires is that the roles of the agents are sort of symmetric with each other. And they're symmetric in this sort of zero-sum sense. And that you have some set of parameters that if you knew, you would then be able to define some measure of the advantage that one possesses over the other. So that's very generic, right? So we could have like actually some examples we've ran. We've trained some reinforcement learning sort of agents to play simplified variants of poker. So that's obviously not a perfect information game.
Very far from perfect information, otherwise it's not such an interesting game.
Yeah.
All right.
And there the x and the y, the attributes that we're using, those are the parameters of the agent. So those are like either the weights or maybe hyperparameters for the training process. And then what we do is like once you have those weights, you can play a whole series of games between agents with different behavior parameters. And there's different probabilities of different outcomes, right? That generates a distribution of possible outcomes. And you define F here to be some moment of that distribution, like expected.
That makes sense.
And then it doesn't matter at all whether the game's perfect information.
Sure. All right, thank you very much.
Yeah, you're welcome.
I also have one question. So you mentioned somewhere like in the abstract that you also use differential geometry of each embedding map to to drive useful information. Can you also talk a little bit about this?
Yeah, absolutely. So that was the end of the talk, and I was hoping I would get a question on that. So this is a picture, like this is an example of applying this technique to kernel blotout. And what you see is, and this was actually one of the examples that drove the desire to have a functional theory, that we get these nice sort of smooth like point clouds. So this is embedding a point cloud into the space, and these scatter clouds are really smooth, and there's sort of obviously some sort of function that this is sampling from.
So when you are saying it's smooth, like, do you have any proof on the smoothness? So what do you mean by smoothness? Like,
so what I mean by smooth here is that, like, if you color so each of the colorings here, I've colored the points by a specific, like, is the specific like attribute. And you can see that these color gradients, there's clearly continuity, right? Yellow moves smoothly to green, and then moves smoothly down to blue, and then moves down to purple. So there's a continuity in the mapping from allocation to this space. If you sample it more finely, you get back the same picture, just in a finer sampling. So as you do a finer and finer sampling, you get out the same shape. It's just essentially graded in more smoothly. And then actually what we were able to do to go back to prove that was, once we built a functional theory, was to explicitly write down what that function was, do that algorithm I'd shown you explicitly analytically, and you recovered a function that these points were sampling from. So what I'm showing you here, in some ways saying it's smooth, that's relying on like pattern recognition of your eye, seeing that there's sort of smooth patterns here. But then the resulting functions that you get, actually these come from, so when I was saying like translationally symmetric games is good to work with Fourier series, you can represent all of these different functions as different Fourier series mappings. So these are smooth, these are differentiable. They're sort of a nice, they're a nice mapping. The reason I wanted to show you this is to show you an example of the type of question that you might ask that could be answered with sort of differential geometry. So each of these embeddings, you could sort of maybe like caricature by recognizing that they all fit somewhere within a triangle, right? There's sort of some sort of generic triangle happening here. And the most extreme trade-off between any agents associated with one of these embeddings is the trade-off between the corners of these shapes. So what you might want to do is to go to one of these corners and then ask sort of what direction in this fundamental kind of disk game space correspond, or if you pick a direction in this disk game space, what does that correspond to in the trait space? So for example, this vector field here that I'm showing you in the background, if I was playing against agent 3 here, no matter where I was in this disk game space, the best response to agent 3 would be in the direction that that vector field is pointing at agent 3. So that vector field tells you about optimal self-play dynamics. It tells you about best responses to other agents. And it also tells you sort of, if I was to write this out, like if this is rock, this is paper, and this is scissors, the continuous extension of that to like a continuous extension around the circle is basically moving in this angular direction around the circle, right? So one meaningful question to ask, that's sort of fundamentally, if you're asking what trade-off does this model, the trade-off is modeled by moving angularly around the circle here. So it would be nice to be able to recover what are those angular directions in the original trait space, because those correspond to optimal self-play responses. They correspond to optimal responses to a particular agent. And that's the type of question that you can answer by actually looking at sort of the differential geometry of the mapping. So if I have a smooth mapping or a differentiable mapping Y, then if I pick some particular direction V in a disk game starting from a coordinate, and you can pick that based on different criteria. So maybe you look for the direction that best represents sort of this circulating flow. You could pick it to be the optimal self-training direction, or you could pick it to be the optimal response direction. These are actually all the same thing. Then you would try to recover a direction in trait space that maps to that direction in the disk game space. And that's the type of thing that you can do exploiting the differential geometry of the mapping. So this has to do, right, with sort of like the tangent spaces of that mapping. In particular, if you can form a Jacobian matrix for the mapping, you can use that to recover directions in trait space that correspond to chosen directions in attribute space. So if I pick some agent or some location in trait space and some subset of disk games, and then I fix the direction V in those subset of disk games that I want to recover, If you look for a corresponding direction W in the trait space that recovers that V, at least locally, all that you really end up needing to do is multiply, sorry, I should say V, is multiply the desired direction V by the pseudo inverse of that Jacobian map. And this Jacobian map actually encodes a lot of sort of relevant information about the game. In particular, you could think that what the Jacobian is doing, the Jacobian is encoding what sort of the fundamental, that angular trade-off direction is in the original trait space. And it's encoding the relationship between those two things. So that's an example where the differential geometry matters here. You can go past this. The curvature in the map has a lot of meaning. Geodesics associated with like the Euclidean distance in the embedded space, those have a natural strategic meaning. There's a lot of ways to sort of pull strategic information from the embedding space back into your trait space if you're able to take derivatives. So if you can use things like the Hessian of the map or the Jacobian of the map.
All right, thank you. Any other question?
So you mentioned something about like going from the trait space to some direction on each disk. Is it easier to go the other way around? So let's say that I know what the disks are, I know what direction the vector field points in. Since all these disks are like orthogonal, if I want to get a best response, do I just like go in each of those directions and add them up?
Yeah, so actually that's exactly what you're asking is the question I was trying to describe, which would be that within the disk games, it's like obvious how to make strategic choices. If I'm competing against Z and I want to do better than Z and I'm starting at Y, the best thing to do is to move in the direction of the vector field at Z.
Yeah.
And so that tells you your self-play dynamic. It tells you fundamentally like, okay, if I'm playing against rock, I should move to paper, right? If I'm playing against paper, I should move to scissors. So it's obvious how to respond to specific opponents in the disc game. It's helpful if you want to build teams. So actually one of the things that Google DeepMind did with this is that if you want to build a team, you want to spread out around the circle so that you can exploit any adversary. In order to do that in practice, you need to be able to take objectives that are in your disk game space, like I'm starting here and I want to move this direction, and turn them back into practical like perturbations of agents that you actually have, which requires adjusting your actual parameterization, right? And that's exactly where this like the pseudo inverse of the Jacobian is relevant, because if you want to be able to go backwards from directions in this space to directions in the trait space, you need to be able to invert the local linearization.
Okay. Thank you.
All right. Any other question? All right. If not, let's thank Alex again. And thank you all for attending. I hope to see you next time on the seminar. Have a good day.
Okay. Thank you all. Thank you, Ali, for the invite.
Bye.